So we have seen that the atomic spectra of hydrogen atom contains various series of spectral lines such as Lyman, Balmer, Bastian, Brackett and Pfund. We have seen what are the N1 values and in which region of the electromagnetic spectrum they fall. Now we will see how can we represent them diagrammatically. If these are the energy levels, so now we will see how can we draw these lines. For Lyman series, N1 was 1. So all the excited atoms will come back to N1 equal to 1, that is the 1 state, that is this N equal to 1. So what can be N2? N2 had the values of 2, 3, 4 etc. So the lines can be drawn like this. Okay, they are falling to N equal to 1. This is called Lyman series. Now if the ground state is N equal to 2, then the excited states will be 3, 4, 5 so on. So every line will fall down to 2, that is the excited atoms will come back to N equal to 2. These series of lines are called the Balmer series. Now if the ground state is N equal to 3, then what will be the lines like? The lines will look like this. So all will come to N equal to 3. This is the ground state now. This is called the Bastian series. Now if ground state is N equal to 4, then the lines will look like this. This is called the Brackett series. And when the ground state is N equal to 5, all the lines will come to N equal to 5. This is called the Pfund series. So we have studied about the series of atomic spectra of hydrogen atom. Now hydrogen has a very simple spectrum. Hydrogen has simple spectrum. For bigger atoms, spectra becomes complex. But some important features were obtained which was common to all spectra. What were the features? The first feature is line spectra for elements, for each element, is unique. Okay, the line spectra for each element is unique. So the line spectra is like the fingerprint of elements. Like our fingerprints are unique for every person, similarly the line spectra for each element will also be unique. And the second feature was there is regularity of line spectra of each element. Now by these observations The first one was the dual nature of electromagnetic radiations, from which we have read both the wave nature and particle nature. And the atomic spectra. Both led to Bohr's model of atom. In 1913, Niels Bohr modified the Rutherford's model and proposed the Bohr's model. Now, the first condition that we need to know about Bohr's model is Bohr's model is applicable only for hydrogen-like systems. Okay, Bohr's model was applicable only for hydrogen-like systems. What are they? Hydrogen atom itself. Now, what is the hydrogen atom? It is written as this, right? So, the atomic number is 1. Z equal to 1 means 1 proton and 1 electron. And what are the hydrogen like systems? Like helium plus. For helium, the electrons are 2. So, for helium plus, what will happen? 1 electron. So, Bohr's model is applicable for single electron systems. Similarly, lithium 2 plus, beryllium 4 plus, beryllium 3 plus, boron 4 plus, and so on. Lithium has an atomic number of 3. So, lithium 2 plus means 1 electron. Beryllium has atomic number of 4. So, 4 electrons were there initially. 3 plus means 1 electron. Boron has an atomic number of 5. So, 4 plus means 1 electron. So, this is applicable for single electron species. Now, we will discuss the postulates of Bohr's model. Before discussing postulates of Bohr's model, we need some important formulas. One formula we know, the Coulombic force, F equal to K Q1 Q2 by R square. The second one is centrifugal force. We have also discussed this when we were discussing about the drawbacks of Rutherford model. Centrifugal force is mv square by r. The next one is angular momentum. Angular momentum. How will we get the value of angular momentum? What is linear momentum? Linear momentum is denoted by P. We know its formula, mass into velocity. Therefore, P equal to mv. So, what will be the angular momentum? Angular momentum will be will have a similarity to the formula of linear momentum. This will be moment of inertia that is I into angular velocity. Angular velocity is omega. So, angular momentum will be I into omega. Now, what is moment of inertia? I is equal to mr square, right? I is equal to mr square and omega equal to v by r. So we get the formula of angular momentum as mvr. So these three formulas of Coulombic force, centrifugal force and angular momentum, we need to remember this before studying the postulates of Bohr's model. So now we will see the postulates of Bohr's model. The first postulate was electrons in the hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. These paths are called orbits or shells or stationary states or allowed energy states. Okay. So in the Rutherford's model also, Rutherford also said that there will be a nucleus and the electrons will move around in the orbits. Now what was the problem? The problem was if electrons move in circular orbits, they will emit radiation. Therefore, the path will shrink. In the Bohr's model, Bohr said that electrons will indeed move around the nucleus, but the circular path will have fixed radius and fixed energy. That is, as long as the electrons are moving in these circular orbits, they will not emit energy. There will be no change in their energies. The change of the energies of these orbits will be constant. And these paths were called orbits or shells or stationary states. Stationary states because these energies are stationary. And allowed energy states. These allowed energy states means all values of energies are not allowed. That is, electrons cannot move in orbits of any random energy value. The electrons will be able to move in orbits having a certain values of energy which are allowed. Orbits can only have certain allowed energy values. This also reminds that the energy levels should be discrete and not continuous. And in this postulate, it was also added that atom has a nucleus containing protons and neutrons. Containing all protons and neutrons. The size of nucleus is very small and it is present at the center of atom. So this particular part has no difference from the Rutherford's model. There will be a nucleus which contains all the protons and neutrons, and the size of the nucleus is very small. Now, the second postulate was the energy of an electron in a particular orbit does not change with time. So the energy of a particular orbit will not change with time, but the electrons can move from lower energy state to higher energy state by absorbing required amount of energy. Also, energy is emitted when electrons move from higher energy state to lower energy state. Okay. So the electrons, when they absorb required amount of energy, they will move from a lower state to higher state, and they move from higher to lower state, they will emit energy. Energy change is not in continuous manner. That is, the energy change will not be continuous manner. They can just move from a discrete energy value to another discrete energy value. So, we will study about the other postulates of the Bohr's model in the next lecture. Thank you.